Welcome to the continuation of our adventure to find the electric field of a ring of charge everywhere in space. In part 1 we derived the solution to electric potential due to a uniformly charged ring everywhere, and in this video we're going to find the expression for the field by taking the negative gradient of the potential. Just as a fair warning, this video will be way more math heavy than the first one, since almost all of the physics was already covered in that first video. But stick around anyway, because the end result will be worth it, I promise. It was shown in the previous video that potential can be written as the complete elliptic integral of the first kind. So let's quickly lay down some extraordinarily basic information on them and some formulas we're gonna be using when deriving the field involving elliptic integrals. As I said before, the elliptic integrals are just some special functions defined as values of certain integrals. They were first encountered while trying to calculate the arc length of an ellipse, hence the name elliptic integrals. Nowadays they are widely used in math and physics and appear as solutions to many physical problems, including the simple pendulum. Yes, you can write down the solution for the simple pendulum without the small angle approximation as a complete elliptic integral of the first kind, just like the potential for the ring. There are two main types of these, the incomplete and complete elliptic integrals. Incomplete ones are functions of two variables, while complete ones are functions of one. There are three kinds of both of them, with forms you can see on the screen. None of them are analytically solvable, but all of them can be expanded in nice power series, which makes the evaluation much easier. The complete elliptic integral of the second kind is actually the one that gives you the perimeter of the ellipse in one quadrant, while the rest are similar, so they're called elliptic integrals too. Obviously there is much more to these integrals, but for purposes of our problem, we are only interested in their form, power series expansions, and their derivatives. Yes, because taking the gradient of a function means taking derivatives. That means we need to know the derivative of the complete elliptic integral of the first kind, and in literature there is a formula for its derivative with respect to the modulus k. And that's it about the integrals, from me at least. Now let's go back to physics. For like the fifth time in these two videos, electric field is the negative gradient of the potential function. I assume you're all familiar with the differential operator nabla. Because we have used cylindrical coordinates to express the potential, we're going to use nabla in cylindrical coordinates as well. When we apply nabla to the potential, we get the following. We need to differentiate the potential with respect to all three coordinates. Let's quickly write down the full potential without the substitutions. We can see that it is independent of the angle phi, which makes sense because there is an axial symmetry, as we have discussed in the previous video. Because the potential doesn't depend on phi, the derivative with respect to phi is 0. Yes! But it most certainly depends on both rho and z, so unfortunately no more cancelling will take place from now on.
Excuse me?
However, since the potential expression is really goddamn long, let's make it a little more user-friendly. The second part is the elliptic integral, and we can write just k of k. The entire first part we can substitute with f of rho and z, because those factors together give us some function of rho and z, while everything else is a constant. So we can write v is equal to f times k. The math will now be so much more bearable to deal with. Let's find the derivative with respect to rho first. By chain rule, dv by d rho is equal to df d rho times k plus f times dk by d rho. We have no formula for dk over d small k, so let's use chain rule again to write the second term as f times dk over d small k times d small k over d rho. Let's now do one derivative at a time. First, df by d rho. Now we need to write down the entire function to see what we have to deal with. We'll move all of the constants out, and we're left with the derivative of 1 over the square root of rho squared plus z squared plus r squared plus 2 rho r. We first differentiate the square root, and then multiply that with the derivative of the term under the square root. So just chain rule again. We end up with the following expression. That was the first derivative term. Now let's do this dk by d rho derivative. We have Rho in both numerator and the denominator, so we'll use the quotient rule. Once we do that, we get the following. And yeah, it looks really nasty, but this isn't even the whole thing, because we need to multiply this with the derivative of the elliptic integral. You can see now why you only calculate the field on axis in your physics courses. But even this isn't the whole thing, because part of this component is also the f by d rho part we did first, times the elliptic integral. Putting everything together, we get this beast as rho component of the electric field. Let's get the z component. We do the same thing as with rho. We write potential as f times k and do the chain rule again. For dk over dz, we do the chain rule like before to get dk over d small k times d small k over dz. Two more derivatives to compute. We take care of df over dz just as with rho, all the constants out, first the square root, then times the derivative of the function under it, and we get the following. Let's now do d small k over dz. There is no z in the numerator, so that's a constant with respect to it and can go out. This is now the same as the previous one, so the result is also obviously the same. And that's what I like. Putting together everything, we get the following for the z component. And now we have found all the components of the electric field. And now you've seen how mind-numbingly long our components alone, but it is finally time to reveal the full expression for the electric field of a charged ring everywhere. And it looks just as hideous as one would expect. I didn't want to put any substitutions back in so you can see it in its full glory. I'm actually going to show you a plot of this field on the xz plane, and I did this both to show you and to show myself that I actually got this right, because this is the exact kind of problem where it's so easy to make a mistake in math. But yeah, comparing this plot to the stuff I found in the literature, it is a very good match, and this is in fact the correct field for the ring of charge everywhere. Thank you for watching these videos. I hope you have learned something new or useful or interesting. And if you liked the video, give it a like, leave a comment if you have any thoughts, questions, or suggestions. Subscribe to support the channel and to get more wild physics in your life. And see you in the next one. Take care.